All right, maybe we can go ahead and get started. So yeah, hopefully you had a good break. We're gonna start off pretty much where we left off in the previous lecture. So we're covering this topic of state estimation, localization, and mapping. And in the previous lecture, we discussed this kind of general framework for doing state estimation known as the Bayes filter. And so this was I guess, follow-on to the technique we had discussed previously, which was the non-deterministic filter. The Bayes filter maintains what we call a belief, which is really just a probability distribution. Over the state space. And as the robot takes control inputs and as it receives more sensor measurements, it basically updates this belief iteratively. So just to remind you of the basic structure of the Bayes filter, at each time step, we have two steps that we do for all states, so for all xt. The first step is what we call the dynamics update. We basically propagate our previous belief, the belief from the previous time step, to the next time step through the dynamics of the system. So we receive or we obtain a new belief, which we call belief bar, at every state. And this is calculated by summing up all the previous states, the probability that you land at xt, given that you are at xt minus 1, and you took control input ut minus 1, multiplied by the previous belief that you had for the state xt minus 1. So this is the dynamics update. And the second step is to take into account the new sensor measurement that the robot receives and update your belief using that. And that's where Bayes rule comes in. Sorry. There should be a belief bar. Divided by P of ZT. And this is the measurement update. And just, I guess, one more piece of terminology. This new belief, this new probability distribution that we obtain once we've done our dynamics update and once we've incorporated the sensor measurement, this is called the posterior belief. And the previous belief, the previous time step, I guess it's called the prior belief. Okay, so this was the general structure of the Bayes filter. What I'm going to discuss today is motivated by a comment that I made at the end of the previous lecture, which is that when your state space is continuous and your control input space is continuous and the measurement space is continuous, these summations become integrals. And doing these computations, so actually doing the dynamics update, actually doing the measurement update, computing those integrals instead of the summations gets computationally intractable really quickly in general. So that's going to be our starting point for today. So we're going to discuss two things today. So we're going to focus on robotic systems that have continuous state spaces, action spaces, and measurement spaces. So the first thing we'll discuss is a particular setting, so a particular set of assumptions where the Bayes filter can be implemented exactly So by exactly, I mean without any approximation. And moreover, we're going to be able to do this computationally efficiently. So the integrals basically that show up in the base filtering steps, it turns out we can calculate exactly, so analytically in a setting that I'll describe. And the second thing we're going to describe is basically an approximation to the base filter. That is broadly applicable. Beyond the kind of specific assumptions that we're going to make for part one. So part one leads to something called the Kalman filter. So if you've taken, I guess, a course in control theory, you may have seen it. I'll just give you an overview of it. The other approach, which works more broadly, so doesn't make the same kind of restrictive assumptions that the Kalman filter makes, is called the particle filter. And these two, so the Kalman filter and the particle filter, are probably the most commonly used instantiations of the base filter when you have systems that have like continuous state spaces and control input spaces and observation spaces. All right, I guess any questions on the setup? Okay, so yeah, let's start with the first part. So what are the assumptions under which we can exactly and computationally efficiently implement the base filter? So it turns out for linear Gaussian systems, we can implement the steps of the base filter exactly. So the reference for this is chapter 3.2 in the probabilistic robotics book. So if you think about what we need in order to implement the base filter, we basically need three things. We need to specify three things. One is the dynamics model, right? So we need to say if the robot is at state xt minus 1, takes control input ut minus 1, what's the distribution over the next state? So that's this quantity over here. So that's one thing we need, the dynamics model, so a probabilistic dynamics model. The second thing we need is some kind of measurement model. So something that says if the robot is at state xt, can we write down a distribution over the sensor measurements that it's going to receive? So that's this quantity over here. And then the third thing we need is some way to initialize the base filter. So we need some initial belief that the robot has. And once we have those three things, we can basically, at least conceptually, run the base filter, like do all the computations. So those are the three things we need to make some assumptions on to make the base filter computationally tractable. So I'll describe each of those things in this kind of linear Gaussian setting one by one. So we'll start off with the dynamics model. So we're going to assume that the dynamics model has the following form. So the state at some time t, so that's xt, equals some matrix at multiplied by the previous state, plus some other matrix bt multiplied by the previous control input, plus an additional term that I'll describe in a bit. So let me call this equation 1. Okay, so this looks very much like the setup we had when we discussed LQR. Right? When we talked about LQR, we looked at continuous time dynamics. So we said x dot equals ax plus bu. Here we're looking at discrete time dynamics. Things are a bit easier in this setting. You can also do everything I'm going to do in the continuous time setting, but just to keep things a bit more straightforward, I'll assume that things are in discrete time. So this is basically the discrete time analog, at least if you ignore this plus epsilon term. This is the discrete time analog of the dynamics we had assumed when we talked about LQR. So the main, I guess, new thing here is this epsilon t. So that's an additive term on the dynamics. Your state nominally evolves linearly, so axt minus 1 plus but minus 1. But then there's this kind of uncertainty or disturbance term. So epsilon t, we're going to think of it as a random variable. So it's something that describes our uncertainty about how the state will evolve. And moreover, we're going to make some assumptions about it. So it's going to be a random variable that's drawn from a normal distribution. So by normal, I really mean Gaussian, so multivariate normal Gaussian distribution. And it has the same dimension as the state. So the dimension of epsilon t has to match the dimension of the state. But yeah, so it's some random variable that has the same dimension as the state and is drawn from a Gaussian distribution. So I guess just to quickly recall, so hopefully this is something you've seen before, but just a reminder, so a Gaussian distribution in the univariate case looks something like this. So it's a bell curve, and it has some mean mu and some standard deviation, so plus minus sigma. So that's the univariate case. More generally, we have some probability density function, so p of epsilon t, which equals, so I'll just write it down here, so the determinant of 2 pi sigma inverse square root, and then the exponential let me just erase this. Okay. I'm missing a bracket. All right, so that's the probability density function in the multivariate case. So mu here is the mean of the Gaussian distribution, and sigma is a matrix. So it's the covariance matrix. So if you have a diagonal covariance matrix, it means that all the elements of epsilon are independent of each other. In general, you could have a covariance matrix that's not diagonal. So there might be some dependence among the different components of the random variable epsilon t. And yeah, usually we denote this so the notation we'll use is n mu sigma. So this is a normal distribution with mean equal to mu and covariance equal to sigma. So I guess just to be explicit, this is some n by 1 matrix where n is the dimension of the state, also the dimension of epsilon, and this is a n by n matrix. And again, in the univariate case, mu is just going to be some single number, the mean of your normal distribution. the covariance is really just the variance, so it's the standard deviation squared. Okay, so that's going to be the assumption on epsilon. So we're going to assume that it's drawn, so it's some random variable. At every time step, you draw some epsilon, you draw some noise, some uncertainty from a Gaussian distribution given by some mu and some sigma. We're actually going to make some further assumptions. So usually we're going to assume, so this is not strictly necessary, but I guess just for convenience, we're going to assume that the mean mu is 0, so 0 bar, meaning that it's the 0 vector. And there's some covariance matrix, which we'll denote as RT. So instead of sigma, we're going to call it RT, the same dimension, so n by n, and potentially changing with time. So at every time step, you might have a different Gaussian distribution, potentially. All right, I guess any questions on this? All right, so the main, I guess the main takeaway is the dynamics are basically linear, but we have this additive uncertainty that's described by a Gaussian. All right, so that's the first thing we need. So this specifies our dynamics model. Right, so for any state and control input, so any xt minus 1, ut minus 1, we now have a probability distribution. Defined by this Gaussian, defined by the dynamics plus the Gaussian random variable, which we're calling epsilon. The second thing we need to specify is some kind of measurement model. Measurement or sensor model. And again, we're going to assume that the measurement model has a linear form. So the sensor measurement at some time t, that's zt, we're going to assume is a linear function, so some matrix C multiplied by the state, plus some uncertainty delta t, where again delta we're going to assume is a random variable, that's a Gaussian. With, again, 0 mean and covariance equal to QT. So this is some matrix that has the dimension of the sensor measurement squared. So the sensor measurement is a m by 1, let's say. Then QT is m by n matrix. So what this is saying is that nominally, so if you ignore the uncertainty, nominally the sensor measurement that your robot receives is a linear function of your state. So you just take your state, multiply it by this matrix C, which of course depends on the specific sensor that your robot has. That's your sensor measurement, except that we have some uncertainty. So we don't know that this is the sensor measurement we're going to receive exactly. We're saying that we receive this without any uncertainty, and then we have some Gaussian distribution which describes our uncertainty about the sensor measurement. All right. Maybe just as a quick check, so I guess what's the mean of the random variable corresponding to the sensor measurement? Sorry, go ahead.
0.
Not quite. So by sensor measurement, I guess I mean this part. So what's the mean of this random variable? I see some answers maybe in the first row, or not. Go ahead.
Should be CT times X bar.
Yeah, it's CT times XT. Right, we're just taking this, which is some vector, and we're adding a zero mean Gaussian on top of that. So if I take a Gaussian, add something to it, I'm just shifting it. And so the mean is just shifting from 0 to CT XT. Okay, yeah, so what this is saying is we have some probabilistic model of our sensor measurements. So at any given state XT, so at any given state xt, we can calculate the probability of receiving a sensor measurement zt given that state xt. So that's coming from this model, linear plus Gaussian. The last thing we need to implement the base filter is the initial belief. So before the robot takes any actions, before it receives any sensor measurements, it has some belief, or it needs to have some belief about its state to basically kickstart the base filtering process. And we're going to assume that this belief, so the belief at time step 0, is also a Gaussian. So its mean, we're going to say, is mu0, and its standard deviation, we're going to say, is sigma 0. All right. Yeah, I guess any questions on any of those three things? So the dynamics model, measurement model, initial belief. Okay. So the main message, or the main kind of trick that makes everything work in this setting, maybe I'll call it an observation. So the proof of this observation, if you're interested, this is in chapter 2.4 in the probabilistic robotics book. So it's a bunch of, I guess, linear algebra, but the observation itself is relatively easy to state, which is that under the assumptions that we've made, so under the assumptions on the dynamics, so linear plus Gaussian, measurement model, linear plus Gaussian, initial belief, just Gaussian. If you make these assumptions, then the belief at some time step t, so the belief over the state at time step t is also a Gaussian. And yeah, this is the main, I guess, fact that makes things kind of nice in the setting. So we start off with a Gaussian belief. So at time step 0, we propagate that through the dynamics of the system, which is linear plus Gaussian. It turns out when you do that propagation, so when you do the dynamics update of the base filter, making these assumptions, you get another Gaussian distribution. You then get some sensor measurement. You apply Bayes' rule. That posterior belief, so once you do the measurement update, that belief is also a Gaussian. So at every time step, you maintain a Gaussian belief on the state. So All right. So basically, the instantiation of the base filter so when you make these assumptions on the dynamics, the measurement, and the initial belief, has a special name, so it's called the Kalman filter. So it was developed, I think, back in the 1960s and remains, like I said, one of the most popular techniques for doing state estimation. So I'll write down what the steps are. I'm not going to go through a derivation. Yeah, because that would take a while. And this is in chapter 2.2.1 in the probabilistic robotics book. So it's, like I said, it's an instantiation of the base filter. So it is the base filter just under the assumptions that we made on the dynamics, the measurement model, and the initial belief. So it's going to have two steps. That we implement at every time step t. So the first step is the dynamics update, the second step is the measurement update. I'm gonna, I guess, just write down the equations, and then we can just analyze them for a bit. All right, so this is the first step. So this is the dynamics update step. So at the previous time step, we had some belief. So let's say the 0th time step, before the robot did anything, we assumed it had some Gaussian belief with mean mu 0, covariance sigma 0. So this part is before the robot takes into account any sensor measurement that it receives at the new time step. So this is the dynamics update. And specifically, this belief bar. So belief bar, again, is when you just do the dynamics update, no measurement update. This belief bar, like I said, is going to be a Gaussian distribution with mean equal to this mu t prime and covariance equal to sigma t prime. All right, so I guess what's the main message here? I think the specific like terms are not super important. The main thing I want to convey is that you can do this computation, right? So you can just like literally type this up in like 2 minutes in Python. These are just like matrix multiplication operations, matrix transpose, and that's it. So at the previous time step, if you had some belief, which is a Gaussian distribution with mu t minus 1, sigma t minus 1, we're assuming that we know the dynamics and that they're linear plus Gaussian, so AT, BT are known, mu t minus 1 is known, the control input that the robot executes is known. Sorry, it should be t minus 1, I think. Yeah, so AT, sigma t minus 1, AT, and RT was the covariance matrix corresponding to the sensor measurement noise, so that's assumed to be known as well. So everything here on the right-hand side is known, so we can just do these matrix multiplications and get our updated belief, which is propagating the previous belief through the dynamics. The second step is the measurement update. Again, I'll just write down the equations. All right, so this has 3 steps. So we calculate this intermediate variable k t, so this is called the Kalman gain. And then from that, we calculate mu t and sigma t. Again, the specific operations here are not super important to the main point I want to make. The main point is you can, again, just implement this in Python, right? So you can use like NumPy to do these matrix multiplications, to do that inverse. And that's it. Like everything here on the right-hand side is known or assumed to be known, including the mean and the covariance once you do the dynamics update. So at the end of this measurement update, you get a belief which is a normal distribution with mean mu t and covariance sigma t. And then you do this at every time step. So you take this new belief, you propagate that through the dynamics at the next time step, you do the measurement update, you receive a new measurement. Sorry, you do the dynamics update, and then you do the measurement update once you receive a new measurement. All right, so just pictorially, it might be helpful to just have a picture in your head instead of the equations.
Is that step 2 sensor update?
So, yes, this one is the sensor update. Yeah, exactly. And the sensor measurement like appears here as you would expect, so that's the ZT. All right, so with pictures, I'm going to draw, I guess, pictures in kind of a univariate setting, so just one-dimensional state space. So let's say this is the state, xt, which is assumed to be a scalar. Let's, maybe just for the sake of concreteness, say that xt equals, let's say, some constant a. Actually, let me even make it simpler. Just xt minus 1 plus some positive constant. Plus some randomness epsilon. So the initial time step, so at time equals 0, let's say our mean is something positive, so it's over here, and we have some standard deviation, some variance for the Gaussian that describes our uncertainty. So at the next time step, I guess so when we do the dynamics update, what is the Gaussian going to look like? Given just under this assumption. So we're saying the state at xt is the state at xt minus 1 plus some constant a plus some randomness. So if we take this initial belief, so let's call this belief at time, let's say xt minus 1. What is our dynamics update going to do, just pictorially? Yes, yeah, exactly. So we shifted by a, And yeah, this uncertainty as well. So there was no uncertainty here. You literally just shifted by A. But then because we have some uncertainty, it's going to inflate the Gaussian a bit. So at the next time step, once we do the dynamics update, actually I guess it's going to be tricky to do this. Let me just do it on the same picture. So we just take this and we shift it. So that's going to be belief bar at xt. So the belief that we get before we've taken into account a sensor measurement, but after we've propagated the previous belief through the linear dynamics. And yeah, I guess with that observation, which I didn't prove, if you want to see the proof, it's in that chapter. But the claim is that once you do the dynamics update and also once you do the measurement update, if you start off with a Gaussian, you're always going to maintain a Gaussian belief. So we started off with a Gaussian, we just shift the mean of the Gaussian and inflate it a bit depending on what epsilon is. And the specific, I guess, mean and covariance that you calculate comes from these equations, which you can implement. Let's say at the next time step, you receive a sensor measurement. So at time step t, you receive some sensor measurement. Maybe that's over here. So I'll call this ZT. So I guess what would you expect the new belief to look like, just qualitatively, like pictorially? So what would the mean look like, for instance? Say that again. Yeah. So it's going to be in between, basically, right? So before we take into account the sensor measurement, we have this belief, so the dotted line. And now our sensor measurement is saying, well, really, I think, well, I as in like the sensor thinks that this is the state. But of course, we know that the sensor is not perfect. So there's some uncertainty associated with the sensor measurement. But the sensor is giving us a hint, essentially, right, that the true state is actually further to the right. So once we do the update, we're going to get something, I guess this orange chalk that I'll use, that looks something like this. So maybe we just shift the belief bar a bit to the right. And we might shrink our uncertainty a bit. Maybe we can think about that as well. So let's say the sensor model, which is up there. So part of the sensor model is this delta t, so that's our uncertainty on the sensor measurements. Let's say qt, in this case, we just have a scalar, so it's a variance instead of covariance. Let's say that qt is very small, so the variance is very small. I guess what's going to happen to the standard deviation and also the mean in that case? Go ahead.
The spread should be less and the dimension should be more towards.
Exactly, yeah. So what we're saying is that we really trust our sensor measurement, right? We have very little uncertainty about the sensor measurement. So the sensor is telling us we're here, we probably are here. So the mean is going to shift more towards the sensor measurement, and we're going to reduce our uncertainty significantly. So this orange curve will have a mean that's close to ZT, and we'll have an uncertainty, so a standard deviation that's very small. Conversely, if we're very uncertain about our sensor measurement, so the sensor model has a high variance or covariance, then we're not going to trust the sensor model that much. So our update, so when we receive a sensor measurement, our update from belief bar to belief is not going to be that drastic because we're saying the sensor is not really giving us that much information. We shouldn't trust it that much. So that's kind of the intuition. Question, yes?
So like for belief bar,
Yeah.
you're adding the epsilon term every time, which is going to make it wider.
Yes.
So does that mean that every single time step your uncertainty is increasing, or does adding the sensor measurement kind of cancel that out?
Yeah, good question. So the sensor measurement does reduce the uncertainty. But actually, there could be other factors. So even with an epsilon, so some uncertainty on the dynamics, we could potentially reduce the amount of uncertainty we have, the standard deviation. I guess you see, maybe it's not totally obvious, but you see an example. I see a hand. Go ahead.
Maybe if it's converging, like if it's a stable system,
Yes.
so that it should converge somewhere.
Yeah, exactly. So if you have a stable dynamical system, so where all the states are converging towards zero, then your uncertainty shrinks. You can kind of just like sit back and do nothing in a sense. Like you can be confident that after a long time, because all states are converging to the origin, let's say, after a while, you should believe that you're close to the origin. So even with this epsilon, it's not necessarily the case that you're going to increase the amount of uncertainty. So it could be that if things are stable, if things are contracting, even with the dynamics, that could help you reduce uncertainty. And then yes, the sensor measurement update like kind of further helps you reduce uncertainty. And the specific like transformations, like going from the belief at the previous time step to the updated belief with the dynamics, and then the updated belief with the measurement, the specifics of like how you update the mean and the standard deviation, like those are given by these equations, but these equations like capture the intuition that I sketched out. Other questions? Okay. All right, so that's the Kalman filter. So the Kalman filter has some pretty strict assumptions. So I guess people have thoughts on when the Kalman filter is maybe not a good, or before that, the question.
Yeah, just a quick question.
Yeah.
So how much the measurement update moves our belief
Yeah.
from U prime, or the average belief from
Yep.
U prime to, or U prime estimate to U prime
Yep.
is dependent on K?
Um,
Like how much does it actually shift over? How close do we get to Z of T?
Yes, so K is this like intermediate thing we calculate to do the update. Push this higher. Where'd it go? Yeah. Yeah, so it's K. K is the thing that's multiplying ZT and CT mu t prime. So yeah, K itself like depends on the measurement model. So QT and let me see. I got the was it? I got the matrices mixed up. I think so. Which one was QT the dynamics or the measurement? I think it should be the measurement. Okay, good. Yeah. So QT is the measurement. So that makes sense. So KT depends on the measurement covariance, and yeah, this update that you do on the mean and the covariance depends on KT, which itself depends on QT. So yes, the change that you make from belief bar to belief is kind of dependent on KT, but KT itself like depends on
So it depends on the measurement error.
yeah, on the measurement.
How much you trust. So if you had no measurement error,
Yes.
you would move it all the way.
Exactly. Yeah. Yeah. I think that's the main intuition. So if you trust your model a lot, so if delta t, let's say the extreme case is where you're absolutely certain, so there's no standard deviation, and let's say like CT is the identity matrix, then you can actually forget about the dynamics, right? You can just trust the sensor. So your sensor, you know, is absolutely like certainly correct. And yeah, in that case, you would collapse all your uncertainty to the sensor measurement that you get. And that, yeah, I guess you can maybe, as a sanity check, you can go through that, compute KT. You might get some divide by zero issues, but you can take limits as QT, this covariance goes to zero. All right. Okay, so yeah, I guess when do you think the Kalman filter is not useful? So it is useful when the dynamics are approximately linear. So if you're hovering we implemented the LQR controller by linearization. So if you can approximate your dynamics kind of in a linear, with a good linear approximation, then the Kalman filter is good. But yeah, I guess what about the initial belief? So the assumption that you have a Gaussian belief on the state. Does that seem reasonable, or can you think of maybe examples where that might break down? All right, I guess maybe I'll sketch out an example. I think the main limitation, at least for robotic settings, is that the Gaussian distribution is unimodal. Actually, I guess maybe before that, let me just make some just quick other comments. This is pointers to additional techniques if you're interested. So if the dynamics are not linear, so nonlinear, we can approximate the dynamics with linear approximations. Which leads to something called the extended Kalman filter. So there's a chapter in the probabilistic robotics book if you want to see that. But yeah, it's basically taking nonlinear equations, linearizing them, and also updating the linearizations as the state changes. But yeah, I think one of the main limitations of the Kalman filter, which is also one of the strengths, I guess, is the fact that the belief is always Gaussian. And hence the belief is always unimodal. So we cannot fundamentally capture beliefs that have two modes or more than two modes. So as an example, just to help us think things through, so imagine that you have a robot with a door sensor. So I guess what I mean by a door sensor is if the robot is close to any door, it can detect that. So maybe it has a camera, it sees that there's a door, and it can basically sense its proximity to some door. And let's say we know that the robot is going to operate in a specific environment. So we're gonna, we have this like corridor, and we know that we're gonna place the robot somewhere in this corridor. And imagine that we have some like Gaussian belief, let's say, maybe with very high uncertainty, so very wide, very large variance. And let's say the robot at some time step, maybe at the very first time step, detects that it's close to a door. So just qualitatively, what should its belief look like once it receives that measurement update? Let's say it doesn't even move, so there's no dynamics update, just a measurement update. What would its belief look like, given that it senses some door that it's close to, or it senses that it's close to some door? I guess maybe I can go ahead.
We would like it to believe that it is either one or the other of the two coefficients.
Yeah.
Because we have Gaussian belief, it must be some meaning, I guess.
Yeah, exactly. So what we want our robot to believe, what we want our robot's state estimate to be, is maybe something like this. right? So we know that it's close to, or it knows that it's close to some door. So it should be pretty confident that it's either close to this door or it's close to this door. And it shouldn't really believe that it's somewhere in the middle. Like it should have like low probability that it associates with being in the middle, because being in the middle is not close to either of the doors. If you have a Kalman filter, then you're kind of like fundamentally committing to Gaussian beliefs. And this kind of belief, like this bimodal belief or multimodal belief in general, we cannot capture well. So we can capture it kind of clumsily, but we can't really capture it well with a Gaussian. So a Gaussian, I guess there are a couple of options. So one option is to do something like this. You can say, this is not to scale, but we can place a Gaussian whose mean is at one of these doors, but that's not really satisfactory because, yeah, we could equally well have been close to the other door. We could do the other door, but that has the same problem. Or we could just split the difference. We could say, okay, like maybe I should think that I'm in the middle, but in some sense that's kind of the worst thing you could do, right? Like just saying, just taking the average of the two doors and putting your probability mass in the middle is almost like exactly wrong, right? Like you know you're not there, and so you shouldn't believe that you're in the middle. So yeah, I guess this lack of ability to capture multimodal distributions is a pretty big limitation for robotics problems. I'll go through some concrete examples. But yeah, so that's what we're going to try to fix with the next algorithm. So we're going to describe a different way to implement the Bayes filter. This time it's not going to be exact. We're going to make some approximations. And this is going to be called the particle filter. And this is chapter 4.3 in the probabilistic robotics book. The main idea behind the particle filter is going to be to give up on exactly representing this belief distribution. What we're going to do instead is approximately represent beliefs. Using samples, which I guess in this context are known as particles. So let's go back to this kind of door example. And let's say we want to represent some distribution that looks like this. So we know that we can't do it with a Gaussian. We could try to parameterize this distribution somehow. So maybe you could write this down as a mixture of Gaussians, but I can come up with other examples where even that becomes a bit clumsy. So we're not going to capture this probability kind of density function exactly. What we're going to do is approximate this distribution with a bunch of particles, so just a bunch of samples. So yeah, maybe something that has a lot of density over here. So a lot of particles, a lot of samples over here, and then you kind of thin out. So the number of particles you have elsewhere is very small. So we're never going to, so with the particle filter, I'll describe the steps in a bit, but we're never going to represent this kind of exact probability density function, this probability distribution. We're always going to be working with samples. So you can think of samples as kind of candidates for where the robot could be. And the density of samples, so if you have a lot of density over here, a lot of density over here, that will represent confidence that your robot is, like in fact, over here or over here. So I guess that's slightly more formally. We're going to maintain a belief over the state with the Bayesian filter, but this belief will be represented as a set of samples. Which, again, in this context, are called particles. So the set of samples at any time t we can denote by st, and it's going to be just a list of candidates up to capital M. Where M is I'm just going to say is large. So exactly what large means depends on the specific problem, but just think maybe 10,000 samples or something like that. Really in practice it's whatever fits on your computer like computationally efficiently. But all right, so yeah, I guess the main point is that we're going to change our representation of the belief. So instead of saying that our belief is going to be Gaussian, like with the Kalman filter, we're going to say that our belief is represented by some set of particles, and we're just going to keep updating that set of particles at every time step. We're going to do a dynamics update, a sensor measurement update, but at every time step, we're not going to explicitly kind of represent some complicated distribution. We're just going to approximate some potentially complicated distribution with a finite number of particles. Yeah, I'll go through the steps of the algorithm, but I guess any questions on that point? Go ahead.
Can you choose like a good initial belief or initial distribution if you don't know very much about your environment?
Yeah, so it kind of depends. If you really know nothing, then you could just spread the particles uniformly across the environment. Usually we know something maybe, like maybe the robot is likelier to be on the ground floor rather than the first floor, things like that. So you could initialize the particles to like roughly match that expectation. But it's like pretty problem dependent. I think it's rare that you really know nothing, but if you truly know nothing, then just uniform spread across the state space. Question?
It seems like as you go through your trajectory,
Yeah.
The optimal number of particles that you might want to use to represent your
Yes.
distribution might change.
Yes, good. Okay, I'll come to that in a bit. Yeah, that's a good observation. So yeah, let me describe the algorithm, and then we'll describe some of the challenges and the variations. Okay, so what I'm going to do is actually play a video. So this is a video that's narrated by one of the kind of main like proponents of particle filters and like main like developers of particle filters in the robotics context. This is Sebastian Thrun, who's also one of the authors of the probabilistic robotics book. So in this video, he's going to give a kind of qualitative explanation of particle filters, which hopefully will give you the main idea, the main intuition, and then I'll describe the formal like steps in the algorithm after that. So I guess here's the video. I think it's about like 3 or so minutes long. So I'm just going to play it, and then maybe we can discuss it and then describe the actual algorithm.
One of the most successful algorithms in artificial.
Actually, I guess, can you hear that at the back? If not, I'll.
So this is a great segue to one of the most successful algorithms in artificial intelligence and robotics.
Can anyone not hear?
Called particle filters. Again, the topic here is robot localization. And here we're dealing with a real robot with actual sensor data. The robot is lost in this building. You can see different rooms, and you can see corridors. And the robot is equipped with range sensors. These are sound sensors that measure the range to nearby obstacles. And its task is to figure out where it is. The robot will move along the black line over here, but it doesn't know this. It has no clue where it is. It has to figure out where it is. Now, the key thing in particle filters is the representation of the belief. Whereas before we had discrete worlds, like our sun and rain example, or we had a histogram approach where we cut the space into small bins, particle filters have very different representations. They represent the space by a collection of points or particles. Each of these small dots over here is a hypothesis where the world might be. It's a concrete value of its x location and its y location and its heading direction in this environment. So it's a vector of 3 values. The sum or set of all those vectors together form the belief space. So particle filters approximate the posterior by many, many, many guesses, and the density of those guesses represents the posterior probability of being at a certain location. To illustrate this, let me run the video. And you can see, in a very short amount of time, the range sensors, even though they're very noisy, force the particles to collect in the corridor. There's 2 symmetrical point dots, this one over here and this one over here, that come from the fact that the corridor itself is symmetric. But as the robot moves into the office, the symmetry is broken. This office looks very different from this office over here, and those particles die out. Now what's happening here? Intuitively speaking, each particle is a representation of a possible state. And the more consistent the particle with the measurement, the more the sonar measurement fits into the place where the particle says the robot is, the more likely it is to survive. This is the essence of particle filters. Particle filters use many particles to represent a belief, and they let those particles survive in proportion to the measurement probability. And the measurement probability here is nothing else but the consistency of the sonar range measurements with the map of the environment given the particle place. Let me play this again. So here's the maze. The robot is lost in space. And again, you can see how within very few steps, the particles consistent with the range measurements all accumulate in the corridor. As the robot hits the end of the corridor, only 2 particle clouds survive due to symmetry of the corridor, and the particles finally die out. This algorithm is beautiful, and you can implement it in less than 10 lines of program code. So given all the difficulty of talking of probabilities and Bayes network and hidden Markov models, you will now find a way to implement one of the most amazing algorithms for filtering and state estimation in less than 10 lines of C code. Isn't that amazing?
All right. Yeah, I think it actually is amazing. I won't set it as a challenge to do it in 10 lines, but you will implement it in the next assignment in Python, and you'll see that it's actually not that complicated. All right, I guess questions on the video before we describe the algorithm? Yes?
So, is the robot given a map of the world before?
Okay, good question. Yeah, so right now we're just focusing on the state estimation question. So in this context, it's called like localization. So the robot just wants to figure out its like x, y, and theta. So we are assuming that it has a map of the environment. We'll relax that assumption in about like 2 lectures, but yeah, at least for now, it's just the state that the robot doesn't know, of itself that doesn't know.
And a second question, is the robot doing like around the block, like while it's trying to figure out where it's at?
Yeah, so the robot is actually doing
So this is a great
the black like curve with the arrow. So the ground truth, like the actual motion of the robot, is that like curve along that curve. So it's not doing a random walk. It's just like going like left and then like into that room, like in this example.
And is that just coming from like external source?
Yeah, I think someone is just like remote controlling the robot in this case. Yes. Yeah. All right. Good. Okay. So yeah, let's look at the algorithm, like the steps of the algorithm. So it has the general structure of the base filter. So there's going to be a measurement step, a dynamics update step and a measurement step. So at each time step, we do these computations. Capital M, again, is the number of samples that represents our belief. So for every sample, what we're going to do is, or let me call it like particles. So for every particle indexed by little m, we're going to sample a next candidate state for that particle. So we're assuming access to some dynamics model, so some model that assigns a probability of getting some state xt, given that the robot was at state xt minus 1 and took control input ut minus 1. So this line up here, that's the dynamics update. So we take every sample, every particle, and we sample some candidate for the next state if you started off at the previous time step at that particle. Additionally, what we're going to do for every particle is compute WT. So this is a weight, otherwise known as importance in this context. And this is what he was referring to as the consistency. So WT for every particle is the probability of receiving sensor measurement ZT. So let's say ZT is the actual sensor measurement that the robot received at time step t. So WT is the probability or likelihood, like the density function of evaluating, density of obtaining ZT, the measurement ZT, given that you are at location xtn. So we're doing this for every particle. So for every little m, 1 through capital M, we're saying what's the likelihood of receiving the measurement that we received, ZT, if we assume that we're at the location specified by this particle. So if WT is high, it means that there was a high likelihood of seeing the sensor measurement that the robot saw, given that it was in location xt. All right, so that's kind of the first block. That's the first for loop. And then we initialize ST. So ST is going to be our new particle representation at this new time step. So we just initialize that as an empty array. And then again for every particle index, so going from m equals 1 to capital M, we draw the index I, or we draw some index I with a probability that's proportional to WT. Right, so I guess before this last for loop, for every m going from 1 to capital M, we had a WT. You can normalize that. You can think of that as a probability distribution over the indices, like over the particles. And in this step, we're basically throwing away particles that have a low likelihood, that have a low like WT. So yeah, I guess just more details on this. So we're drawing capital M samples with replacement. So we're not like throwing things away once we draw a particle. So we're drawing capital M particles with replacement from the set of particles that we had after we did the dynamics update. And so yeah, I guess the main intuition is that we're getting rid of particles with a high probability if they have low importance. So if they were not consistent with the sensor measurements, if WT was small, then there's a low probability that they're going to be sampled in the second block. All right. I guess questions on this? Go ahead.
So that means like over time the number of samples is consistent?
Yeah, so the way I've described it here, over time, the number of particles we represent is always consistent. We're going to get more and more kind of duplicates, right? So you might have multiple particles at the same exact location, and that's perfectly fine. That's allowed by this. And that means that we're very confident. If we have lots of particles at the exact same location, it means that we're very confident that the robot is around that location. Question?
So if you're going through like a real house that doesn't have a ton of actual symmetry,
Yes.
wouldn't you know pretty precisely, like your belief would always just kind of be one position roughly?
Exactly, yeah. So it would pretty quickly like coalesce. Like the belief would like pretty quickly concentrate around one location. And I guess that's what we want ideally. I think it's interesting that the particle filter like has this ability to represent like multimodal beliefs, which might be important at the first few time steps that the robot operates in. But then you would hope that if the sensors are good and if your environment doesn't have a lot of symmetry, then you get pretty confident about where you are pretty quickly. All right, other questions on the algorithm? I'm happy to go over it again or clarify anything that's unclear.
Throughout, and maybe especially at first,
Yeah.
are you sampling uniformly from the state space?
So at the initial time step, before you see any measurements, you have some initial belief about where your robot could be. And I guess that was related to the question about like how you choose that initial belief. If you have some knowledge about where the robot is likely to be, then you could have more particles there. If you have no knowledge really about where the robot is, then you just sample uniformly. And then you go through these steps. So you take all of your particles, you propagate them through the dynamics, you calculate these weights, which tell you how likely the sensor measurement was to be received from a given location, from a given particle, and then you throw away particles using this kind of resampling step. So you sample particles that have a high weight with high probability. Question?
Is the reason we're saying we're getting bigger samples because we're sampling like a discrete number of particles? Like,
Yes, so we're sampling, so this second block, like the second like for loop, we're sampling with replacement. So we have capital M particles, and we're capital M times drawing samples from that set. But we're drawing with replacement. So we can take one particle out. So let's say this particle like 10 has a very high W. So we might like sample like particle 10 like a bunch of times. So if we sample particle 10 a bunch of times, it must mean that we're not sampling other particles which have a low weight, so we're throwing those away. So that's kind of the mechanism for like concentrating our beliefs in the particle filter. Does that make sense?
yeah.
Okay, all right, good. Other questions? Okay. Yeah, so I guess if you're interested in more details, chapter 4.3 is the reference for this. I just want to clarify some notation as well. I think this in the past has caused some confusion. So difference in notation between like the tilde, which what I mean here is that you sample something from a distribution. So if you assume that your robot was at xt minus 1 superscript m, so the previous time step, and took control input ut minus 1, we're assuming that we have some probabilistic model, right? So linear plus Gaussian or something more complicated. So we can sample some particular state from that conditional distribution. So that's the tilde notation. The second thing is the computation of the W. What we're doing there is evaluating the density function of the sensor measurement model. So we're saying how likely is it that we received the sensor measurement ZT if the robot was in fact at state xt superscript m. So yeah, I guess these have kind of different like semantics. Like one is sampling from a distribution, the other is evaluating the probability density function. I guess questions on that? Okay. All right. So yeah. Okay. Now we can get back to this question about variance of the particle filter and maybe like changing the number of particles we need at every time step. So what I described is the kind of vanilla version, the most basic version that it makes sense to start off with if you're encountering a new problem. As I mentioned, this is one of the most like popular algorithms in robotics for doing state estimation, and particularly in the context of localization, which is the problem of figuring out where the robot is in some environment. So someone asked, I guess, whether we're assuming we have a map of the environment, which in this video, the robot had some like knowledge of the geometry of the environment that it's going to operate in, so how the rooms look like and so on. And all it's doing is updating its belief about where it is as it receives more sensor measurements. Later on, we're going to also extend this to doing mapping. So where the robot doesn't know what the environment looks like, it doesn't know where it is, so it has to both figure out kind of where it is and also what its environment looks like. So it's simple to implement and works quite well, but it has some limitations. So specifically, the state space dimension is very large, or if the beliefs need to be extremely complicated, so many different modes in a high dimensional space, then you might need lots and lots of particles to get a good approximation of the belief. And there are like clever like variants where you sort of re-sample or regenerate particles or increase the number of particles you represent as like time gets as sort of time moves forward. So if you see that the belief is getting more and more complicated, then you could sort of adaptively increase like capital M, the number of samples that represent your belief. So that's definitely one of the kind of popular like tricks. There's a bunch of tricks that people have come up with to get particle filters to work well, and some of them are described in the chapter I referenced in the probabilistic robotics book. I guess does that sort of address your question? Okay, good. Okay, yeah, any other questions on this? All right, so I'll see you on Thursday.